Hello and welcome. After some comments on my recent culling video and discussions about the performance of different approaches to threading, I thought it would be good to run some empirical tests to compare the results. I did not want to run the tests in isolation, but rather as part of an actual complex real game setting, where lots of other calculations happen before, after, and in between the tests. This highlights a few very interesting factors to keep in mind when planning a multi-threaded approach. Let's have a look. The canvas for our tests is a large world with random land masses, containing over 1.5 million static meshes and thousands of animated units walking around on it. Each herd searches for a new random target hex nearby and recalculates its flow field for that hex once per second, while each unit walking along the road network searches for a random new connected target node every time it reaches its destination. Also, all the over 90,000 hexes propagate their climate once every 10 seconds, while clouds and snowstorms continuously update their local climate. This ensures that there are various calculations happening per frame throughout. We'll see later how the different jobs have been configured and what calculations are actually performed, so stick around for the code if you're interested. For now, let's jump straight into a few results to get a feel for what we'll be testing. However, remember that context is very important, and we'll see that many factors play a role in the rank ordering of what works best in a specific scenario. So don't base your conclusions on these first results. There are some more on the way. It reminds me of the politician saying, "These are my principles. If you don't like them, I have others." We start off by timing how many milliseconds it takes to run the entire job on a single worker thread. And it's around 25 milliseconds for the C# compiler and around 20 milliseconds for the burst compiler. This relatively modest improvement already indicates that the job we're running here isn't very well suited to burst compiling. But let's go with it for our first set of results. Next, we compare two different ways of setting up our native containers for multi-threading. In the first case, we create a separate native array for every variable we want to cater for, while in the second case, we first create a struct containing all variables, then create one native array for the struct. The important difference is how the memory is packed. In the first case, all the integers are packed one after the other, all the floats are packed one after the other, etc. In the second case, one instance of an integer, float, float4, and matrix form a chunk of memory, and all of these chunks are packed one after the other. We express each job's running time as a percentage of that of the multi-thread, multi-array case, so that we can easily compare results. There does not seem to be a big difference between the C# performance of these two cases, with the struct being ever so slightly slower. We may also want to conclude that the burst compiler does slightly better than the C# compiler. However, there is another important factor that we need to cater for first. We see that if we swap the order in which the jobs run around, the performance varies considerably. Sometimes the burst compiler does better and sometimes worse. Sometimes the many native arrays job does better and sometimes worse. What's happening here? I'm not going to go into much technical detail, but in summary, there are various memory caches between the RAM and the CPU, each one becoming faster but also smaller. The CPU tries to optimize which memory to store in these caches, giving priority to data that is used most frequently as well as most recently, to try and minimize the time it takes to fetch the data from memory. I assume that, in some cases, if two jobs using the same data run one after the other, the second job could run faster since it benefits from the work already done by the first job to bring the memory closer to the CPU. But I've also found that being the first of the jobs to run sometimes improves performance. There's a lot going on having different impacts, but it's clear that not all of the gain of parallel processing comes from the burst compiler or from the difference between many small native arrays versus one large native array. A lot can be attributed to the memory management. Since we cannot control cache management, I've tried to negate this impact by running the jobs in a completely random order every time. We see that the differences are now less pronounced, since the jobs share the best turns and the worst turns between them. Finally, we add a struct version that uses pointers to reference the memory directly. I didn't expect much performance gain for the job itself, since I expect the way the memory location is obtained internally from the native array index to be very similar to manually adding an offset for the index onto a pointer indicating the starting position of the native array. Still, there is a slight increase in performance. Also, I suspect that using pointers and writing straight to the memory of an element of the struct could be useful where you want to change only part of the struct without having to create a complete new struct with only one element changed. I'm definitely going to test that out in my game. Before we look into the code of creating these different jobs, let's consider one last interesting result. Up to now, we've run all the tests every frame. If we only allow one test per frame and cycle through them, of course the game runs faster since there is less to do each frame. However, we find that each one of the jobs runs considerably longer than before. Since nothing has changed in the calculation itself, the reduction in performance can be attributed to the memory management. The data used in each job is now given lower priority when filling the caches because it is not used as often as before, causing the memory lookup to take longer. Of course, there will be an improvement in performance for the other jobs in the game that still runs every frame, since their data can now use more of the cache. Up to now, we've been running at 30 frames per second. Something interesting happens as we slowly increase the frame rate by scrolling away from the action. The jobs run more frequently, and as a result, they become increasingly faster again, as their memory is given a higher priority in the cache again. So, we've seen that the cache management has a significant impact on the job performance, and that the burst compiler adds some speed to this example that isn't very well suited to it, but that the three options for accessing the native memory aren't actually all that different. So, let's see how the jobs are set up. First off, we allocate 4 individual native arrays of 500,000 elements each, an integer, a float 4, and a 4x4 matrix. We also create a struct containing each of those variables with a native array for it. Next, we create instances of the jobs that will be applied to this memory and link the native arrays to them. We also create a burst compiled version for each job. For the jobs referencing a pointer to the native array of the structs, we need to enclose the code in an unsafe block, since you're basically telling Unity, give me the steering wheel and stand back. In terms of the calculations performed by each job, we have a few basic multiplications, power functions, and the creation of a matrix from position, scale, and rotation values dependent on the index being processed. These are the same across the jobs. The first job allocates the results to the separate native arrays, while the second populates the native array of structs. The third job first obtains a pointer to the element at the index being processed, and then alters individual variables of the struct. You can also obtain a pointer to a variable in the struct, and then alter its elements individually, giving you fine control over exactly what gets altered. Finally, for the burst compiled versions, the code is exactly the same. We just add the burst compile attribute as a header to each job. Scheduling and timing the jobs is straightforward, with a bit of jumping through hoops to randomize the order. We use a built-in stopwatch and cater for cumulative times so that we can calculate an average time over many frames. The final result we will consider is one where the job is a lot more complex. Up to now, we've had 500,000 elements, but the calculations for each element was fairly light. If we have more complex calculations for each element, the burst compiler can have a bigger impact. Here you can see the difference between running the culling job from my previous video with and without burst compiling. The burst version takes only between 64% and 71% of the time that the C# version takes, depending on the view, which allows us to do a lot more culling per frame before the frame rate starts to get choppy. Of course, the more suited the calculations are to burst compiling, the more gain we can achieve. I'm sure there are specifically selected examples with crazy impressive gains out there, but for a real game example, I think we did pretty well. And that's it for this video. Please subscribe to this channel, wishlist and follow Minor Deity on Steam, or join the Discord server to stay up to date. All the links are down below. Thanks for your time and support.